welcome to the ATAR Notes lectures for September 2023 for Mathematics Extension 2. I hope you guys are all doing well. Hope you guys are all keeping up with the madness that is the HSC, and I hope you guys are enjoying the course at least to some degree. So without further ado, I think we can jump into the content. And as a side note, atarnotes.com, check that out when you get a chance. Plenty of free resources on there. I found it personally useful when I was a student, and I hope you guys find it useful as well. So yeah, check that out when you get a chance. Plenty of free resources on there. I found the study notes extremely useful because it was compiled by many of the top students in the state, or like many of the top students who did quite well. Videos as well, I found those quite useful, and the lectures, of course, I've attended pretty much all of them. So yeah, Mathematics Extension 2. So yeah, I'm Rohan. Just a bit about me. I'm currently completing a double degree in engineering and science at UNSW. I'm majoring in civil engineering for the engineering part of my degree, and majoring in physics for the science part of my degree. I graduated back in 2022, so that was last year, with an ATAR of 98.3. So the subjects I did during my HSC was Mathematics Extension 1, Mathematics Extension 2, Physics, Chemistry, Design, Tech, and English. And out of those, my favorite was obviously Mathematics Extension 2. So just as a side note as well, I was a student in the TuteSmart program. I greatly enjoyed the program, and I found it quite useful, and now I'm a tutor here. Okay, so in terms of today's lectures, it's going to mainly involve a whole bunch of problems from different syllabus dot points, which will cover hopefully multiple syllabus dot points within each question. And so the topics to be covered are complex numbers, further integration, proof, vectors, mechanics, and in the end I'm going to throw in some exam advice. Have a think about that as you go in through the exam. So these questions, some of them come from the past HSC papers, some of them come from the NESA sample paper, and some of them come from just other resources. So yeah, let's get started. Let's start with some complex numbers then. Okay, so with complex numbers, we know that the questions can range from E1 to E4 levels of difficulty. And so what I mean by that is, for E1 type questions, you have your add two complex numbers, multiply two complex numbers, divide two complex numbers, those sort of things, your question 11 earlier on, that sort of question, which isn't too difficult. But E4 levels of questions do turn up in terms of complex numbers as well. So towards question 16, there is a chance that you might see some complex numbers. So something like a geometric proof or an algebraic proof or something along those lines. So yeah, make sure that you're familiar with the concepts and workings of complex numbers. So what I mean by that is make sure you know what happens when you multiply two complex numbers, what happens when you divide two complex numbers, what happens when you add two complex numbers, or geometrically, hopefully. Geometrically is probably simplifies a great deal of the questions quite a bit. And these properties as well. Some people tend to memorize them just straight like that, but I would recommend having an understanding of the actual geometric meaning of multiplication and addition and all that sort of stuff on the complex plane, and these sort of properties just sort of immediately fall out from that. So yeah, let's get started with a geometric example. So we've got the points A, B, C, and D, and they all lie on the Argand diagram representing complex numbers A, B, C, and D respectively. The points form a square as shown on the diagram by using vectors or otherwise show that C equals 1 plus I times D minus IA. Okay, so let's have a look at the question again. Yeah, okay, so now if we look at these two vectors AD and BC, we can see geometrically what do we have to do to AD in order to turn it into DC? Well, because this is a square, this angle in here must be pi on 2 radians, right? Or 90 degrees. So in order to turn that into, turn vector AD into DC, all we have to do is rotate AD by 90 degrees, or pi on 2 radians. Is going to form DC. AD rotated by 90 degrees is going to form DC. Now, what does that mean in terms of complex numbers? What do we have to do if we want to rotate something a complex number by 90 degrees, what do we have to do to it? Well, we have to multiply that by I. So multiplying I by AD, so we want to take this for AD, rotate it by 90 degrees. If we want to do that, AD is the same as saying D minus A. And vector DC, because that forms DC, we can say that's equal to C minus D. Now, if you go back to the original question, you'll see that it's going to want an expression for just C by itself. So we'll do that by just rearranging, making C the subject of the equation. So we're going to end up with D plus I times D minus A. And then just expanding that out, we end up with D plus ID minus IA. And then from there, we can factorize out a factor of D, and we end up with 1 plus I minus IA. And so we've concluded that C equals 1 plus I times D minus IA as required. So yeah, not too difficult of a problem, just a bit of observation geometrically, and then playing with the algebra a bit. So yeah, that wasn't too bad, and I think we can jump back to the questions. Second question. This one also a bit geometric, but the second part's going to involve a bit more of the algebraic side of things. So we've got a complex number z1, and then we've got another complex number z2, and it's related to z1 by the equation ETI pi on 3 times z1 is z2. And the diagram shows points A and B, which represent z1 and z2 respectively in the Argand diagram. Explain why the triangle OAB is an equilateral triangle. So because we know that Z2 equals Z1 times ETI pi on 3, what does that mean geometrically? Well, if you think about the triangle, if I redraw the triangle, let's just get Notepad up. So for question 2, if we redraw the triangle, Z1 looks something like this, Z2 looked something like this, and we know that Z2 equals Z1 times e to the I pi on 3. Well, what does that mean? Well, in terms of multiplying by just e to the I pi on 3, that's just the same as rotating by 60 degrees, right? Because when we multiply by a purely complex number, a complex number which has a modulus of 1, that means that it is just a pure rotation. So this angle in here must be pi on 3, if this one's Z1 and this one's Z2. Okay, and what else do we know about Z1 and Z2? Well, because e to the I pi on 3, this value here, is a pure rotation, Z1, the length of Z1 and the length of Z2 have to be equal, because we're not scaling it up by any factor, we're just rotating it. So that means that on our diagram, we can mark on that this length is the same as this length. And because the length of Z1 is the same as length of Z2, that means that triangle OAB is isosceles. And because we know it's isosceles, that means these two angles in here, that one and that one have to be equal. And because the whole thing has to add up to 180, the only possible values of those two angles are pi on 3 and pi on 3. So that means that the triangle must be equilateral because it's got 3 sides of 60 degrees, 3 angles of 60 degrees, so it must be equilateral. Yep. And that's pretty much the answer. You should also make a note about why these are pi on 3. It's just a matter of going pi minus 2 times, we'll call the angle alpha, for example, and that should be equal to pi minus 2 alpha minus pi on 3 should be equal to 0, right? Because all the angles should add up to 180, and then that would show that alpha equals to pi on 3. Okay, so that wasn't too hard. We've proven that it's an isosceles triangle. The second part of the question says something like, prove that Z1 squared plus Z2 squared equals Z1 times Z2. So the second part of the question says, prove that Z1 squared plus Z2 squared minus Z1 Z2 equals 0. Okay, so this question, there are a couple of ways of going about it. One of them is just to have z1 squared plus z2 squared minus z1, z2, and put in the values of z1 and z2, or like leave z1 as it is, plug in z2 equals z1 e to the I pi on 3, and then doing a bit of algebraic manipulation. You're going to have to convert it back into cos theta plus I sine theta form, and then doing a bit of algebraic manipulation will show that this holds. So, yeah, another way of stating this is this, z1 squared plus z2 squared equals z1, z2. So yeah, just subbing in the left-hand side, subbing in the right-hand side, and then showing that they're equal will work, but there actually is a bit more of a clever way to go about it, and that is as following. So we know that z2 equals e to the I pi on 3 z1, right? And what happens if we cubed both sides of the equation? Well, we would end up with z2 cubed equals e to the I pi, because the 3 and 3 cancel, and we're going to end up with a z1 cubed. Now, e to the I pi is just going to be negative 1. So then that's just going to leave us with negative z1 cubed equals z2 cubed. Right? And another way of writing that is just to bring everything onto one side, and we're going to end up with z2 cubed plus z1 cubed equals 0. Now, the way you can factorize this equation is to say that that's equal to the same as z1 plus z2 times z1 squared plus z2 squared minus minus z1 z2, and that's equal to 0. Now, how did I know this? It's the sum of two cubes of factorization. Feel free to check that expansion when you get a chance, but this is something that you should be somewhat familiar with, although it's not like specifically described or talked about in the syllabus. Just be familiar with the difference of or the sum and difference of two cubes factorizations. It's like, you know how we often talk about the difference of two squares? Similarly, this is the sum of two cubes being factorized. Now, there are two solutions to this equation. Either z1 plus z2 equals 0, or this thing equals 0. Can z1 be equal to negative z2? Because if z1 equal to z1 plus z2 is equal to 0, z1 minus z2, z1 has to be equal to negative z2. Can that be true? Well, clearly, since z1 is equal to, z2 equals z1 e to the pi I on 3, z1 cannot be equal to z2, right? So, since that. And so the only solution that we're left with then is to say that z1 squared plus z2 squared minus z1 z2 equals 0. And another way to think about why z1 cannot be equal to negative z2 is just if you go back to the diagram, clearly z1 is not equal to z2 because it's rotated by pi on 3. Yeah, and then if we rearrange this expression, we're going to end up with z1 squared plus z2 squared equals z1 z2, and so we're done. We've proven what they wanted. Yeah, so that's sort of the cleverer way to go about it. This is probably the easier way in terms of the number of steps, but then sometimes in an exam situation, if you're not able to see that, just subbing in left-hand side, subbing in right-hand side will eventually work. It just takes a few more steps and a bit more conversion to cos theta plus I sine theta form. Okay, let's jump back to the questions. Yep. Okay, this one's a bit trickier. This one involves polynomials and involves the cube roots of unity. So yeah, let's have a look at this one. Consider the polynomial Pn of x, which is equal to x plus 1 2 to the n plus 1 plus x to the power of n plus 2. Let omega be a cube root of unity, and omega is not equal to 1. By considering Pn of omega and Pn of omega squared, prove that x squared plus x plus 1 is a factor of Pn of x. Now, if they've said that that omega is not equal to 1, that means that omega must be a complex root of unity. So we can use that in order to come up with the proof. So let's go to question number 3. And first step is to recognize that when we have omega cubed equals 1, right? We can factorize that, or we can rearrange that to say that omega cubed minus 1 equals 0, and we can factorize the left-hand side of that by using the difference of two cubes formulas. So like I said, not something that's particularly discussed explicitly in the syllabus or discussed explicitly, I mean, in my experience during high school, but definitely something that you should be familiar with because it does seem to turn up here and there in questions, even in like the 2 or 3 questions that we've done, it turned up twice. So yeah, be familiar with it somewhat. Omega minus 1 times omega squared plus omega plus 1 equals 0. That's the difference of two cubes factorization for omega cubed minus 1. And so omega is not equal to 1, right? So then this solution is not, it cannot be considered. Then the only solution is to say that omega squared plus omega plus 1 equals 0. So that means that 1 plus omega squared equals 0. And now we're going to have to come back and keep using this expression because as we go ahead and use the polynomial, we're going to see different terms or different sections of this expression turn up, and we're going to have to sub that in eventually. But first, let's go ahead and sub in Pn of omega. They've sort of hinted to us that we're going to have to consider that, so let's do that. Pn of omega is equal to omega plus 1 to the power of 2n plus 1 plus omega to the power of n plus 2. Just subbing it in to the polynomial. Okay, so omega plus 1, if we have a look at this, this is the same as saying omega plus 1 equals negative omega squared. And we can actually substitute that in, and that's going to give us negative omega squared. We're going to replace the omega plus 1 with a negative omega squared and leave everything else as it is. And if we go ahead and expand the bracket, or expand the brackets, we're going to end up with a negative, because 2n plus 1 is always going to be odd, right? No matter what n you're going to put in. Negative 1 to the power of an odd number is still going to be negative, and then the omega to squared is going to turn into a 4n plus 2, and then we're going to have an omega n plus 2. Okay, so from there, I'm going to go ahead and factorize out an omega n plus 2, and you'll see why, because we're going to end up with an 1 minus omega to the power of 3n. And what does that mean? Well, if we've got a 1 minus omega to the power of 3n, we know that omega is a cube root of unity. And because even if you multiply, so we know that that's true, even if you take both sides to the power of n, it's still going to be 1. So then 1 minus omega to the power of 3n is going to be 0. So that means that this thing inside the brackets is also 0. So this entire expression must be 0. So we know that Pn of omega equals 0. Now, coming back to Pn of omega, we can do something similar with Pn of omega squared. So we'll do that. We'll sub in omega squared. And that's going to leave us with 1 plus omega squared to the power of 2n plus 1 plus omega squared n plus 2. And 1 plus omega squared, where have we seen that before? Well, we saw 1 plus omega squared back here. If we have 1 plus omega squared, that's the same as saying negative omega, right? Because if we just rearrange this expression, we can come up with this expression. 1 plus omega squared equals negative omega. And so once we've gotten that, we can go ahead and show that that's going to be equal to negative omega to the power of 2n plus 1 plus omega squared to the power of n plus 2, just leaving that alone. And doing a similar factorization, we see that we can pull out a factor of omega to the power of 2n plus 1 here, and we're going to end up with a equation minus 1 plus omega cubed equals 0. Minus 1 plus omega cubed. And because we know that omega cubed is just going to be 1, we know that this thing is just going to be 0. And because we know that when anything multiplied by 0 is 0, we know that Pn of omega squared is also 0. Pn of omega squared must also be 0. Now, what does that mean? Well, if something's equal to 0 when we sub it into a polynomial, it must be a root of a polynomial. So that means that if we have x minus omega, right, that must be a factor, and so should x minus omega squared. Should be factors of p of x, right? So p of x is divisible by these two expressions. Now, what happens if we multiply them? Well, we'll see that we have x minus omega times x minus omega squared is going to give us x squared minus omega squared x minus omega x plus omega cubed. Now, if we pull out a factor of minus omega here, we're going to end up with, factor of minus x here, we're going to end up with omega squared plus omega, and then plus omega cubed here. And we know that omega plus omega squared is just going to be equal to -1, because 1 plus omega squared, so 1 plus omega squared equals 0. We showed that earlier. So omega plus omega squared must be equal to -1. And because that's equal to -1, that's going to be x squared plus x, and omega cubed is just 1, so x squared plus x plus 1. So that means that x squared plus x plus 1 is a factor of p n of x, and so we're done. Okay, so coming back to the questions again, although that was a bit of a tricky question, we reused that expression 1 plus omega squared a couple of times. So sometimes in some questions you might have to reuse the same expression a few times. So keep that in mind. Whenever you come up with an expression, especially with cube roots of unity, the 1 plus omega squared expression seems to turn up a lot. So make sure you're familiar with that. And yeah, using that, we considered Pn of omega squared. We showed that those two are factors, and we multiplied them together to get x squared plus x plus 1, and we showed that that must also be a factor of Pn of x. Okay, so not too difficult, but for 4 marks in terms of the number of steps, but being able to see that is definitely something that comes with practice. Being able to see that we need to reuse that expression. Okay, now sketch the region defined by pi on 4 is less than or equal to argument of z, less than or equal to pi on 2, and imaginary part of z is less than or equal to 1. This isn't too complex of an example. It's just sketching regions of a complex plane, which is fairly a stock standard sort of question that should turn up maybe question 11, 12-ish. So if this is our complex plane, the line, because we've limited the argument between pi on 4 and pi on 2, we're going to have to draw in the line pi on 4, which is going to look something like this. And we leave an open circle at 0 because the argument is no longer defined at 0. And so we're going to have a line of pi on 4 here with an angle of pi on 4 to the horizontal. And so all this region, anything beyond that would be included. But they've added another, so anything with an argument beyond pi on 4 would be included, but then they've added another limitation on the region, and that is to say that the imaginary part of z is less than or equal to 1. And because it's less than or equal to 1, that means that we've got 1 here. So if we draw in a line like this, then all this region is what's considered. So none of this region would be, but all that region is what's included within the region of the complex plane defined by this relationship here. Okay. So now onto some further integration. Differentiation computations are easy, integration ones not so much. Now with differentiation, you've got sort of a set number of rules which you can apply over and over again, or use different ways, or like sort of manipulate around. But with integration, there's quite a few different methods that you could go about doing them. Sometimes it's not even directly integrable, as in integrable, as in it's not, you can't do it analytically. So yeah, this is just a bit of a joke in terms of integration comparison with differentiation. Okay, so the methods which are covered in the syllabus, in addition to those covered in extension 1, are algebraic manipulation, substitution, partial fractions, integration by parts, and then these are then maybe further applied, particularly integration by parts, to derive recurrence relations. So that's sort of an outlook of the further integration topic. Algebraic manipulation in itself isn't in particular a integration method, but it does come in handy quite often. So yeah, be familiar with that. Okay, so substitution as well. Just a side note on substitution, in extension 1, you will always be given the substitution to use for the integral. In extension 2, it's quite often that you're going to have to come up with substitution yourself. So this sort of thing comes with a lot of practice again, and being able to, oftentimes it's just subbing out the ugly part of the integral, some people say, but yeah, that's just something that comes with practice. So let's try a question. And before we do that, so all that's necessary is some clever algebraic work. So sometimes there's the add subtract trick or the multiply divide trick, where we're adding and subtracting the same thing, or multiplying and dividing by the same thing. So that's the same as adding 0, so that shouldn't change the question, and multiplying by 1 should also not change the question. Sometimes you might have to complete the square, particularly when there's quadratics involved, and sometimes polynomial long divisions involved. Partial fractions is what we're going to cover following that, but first let's look at completing the square sort of things. So here's just a brief outline of completing of solving these sort of integrals, which look like this. I won't spend too much time on that, so feel free to have a look at this in your own time, but I think we can move on to some questions. Okay, so we've got the integral of 1 over 1 plus root x. So that's our next integral. So question 1. So we've got the integral of 1 over 1 plus root x dx. Okay, so when we see this integral here, immediately you look at this and say, well, it's not a sort of well-defined or like a known integral, as you would say. It's definitely something you're going to have to do some work on. So let's try and use some u substitution. So we know that u equal root x, and the reason we do that is because we want to try and, usually the way I try first experiment is see if there's a derivative in there, which I can eventually sort of use as the du dx relationship. Or the other way I do it is just to see if there's an ugly part, which I can sub out, and in this case the somewhat ugly part is the u equals root x. So what I'm going to do is let u equals root x, and so that's going to be the same as saying x to the 1/2. And then we can take the derivative, du dx, and that's going to leave us with 1/2 x to the minus 1/2. So the same as saying 1 on 2 root x. And because we want dx, and there's no root x's in the integral, we're going to flip both sides. We're going to now get dx on du equals 2 root x. Now, technically, derivatives aren't just reciprocating, right? Technically, there's more going on behind the scenes, but thankfully, we can actually just treat them like fractions, but they're not fractions. We need to make sure that we understand that. So dx equals to 2 root x du, and then we can put that back into our integral, which I'm going to name I just for convenience. So the integral is going to be 1 on 1 plus root x times 2 root x du, just replacing the dx with a 2 root x du, and then I'm just going to pull out the factor of 2 in the front, and so we're going to end up with 2 times root x over 1 plus root x du, but we know that root x is our u, so we're going to sub that in, u over 1 plus u du. Okay, so now you look at this integral and you go, okay, if the bottom was the bottom is very similar to the top. All we're off by is a constant of 1. So what we're going to do then is use some algebraic manipulation, or like just the add subtract trick. So we're going to add 1. And because we've added 1, we're going to have to subtract 1. So you see how we've made no difference to the original integral? We've just rewritten it as that. So that's going to leave us with 2 times the integral of 1, because u plus 1 over u plus 1 is just 1, and then minus 1 over 1 plus u. Now that's definitely a very easy integral, because the integral of a constant is just going to be, like for 1 it's just going to be u, and the integral of that is just going to be an ln. So we're going to end up with 2 times u minus ln 1 plus u. And then u, remember it was just root x, so we'll sub that in. 2 times root x minus ln 1 plus root x. And so we can go ahead and say that then our integral equals 2 root x minus 2 times ln 1 plus root x plus c, and don't forget the plus c like I did there, plus c. And before we finish off the question, we notice that what's inside the brackets here, this 1 plus root x is never going to be negative, and 1 plus that is never going to be negative, so we can get rid of the absolute value brackets, and we're going to end up with 2 root x minus 2 times ln 1 plus root x plus c. And so we're done. That's the value of that integral. So not too difficult, just a bit of a u substitution and then a bit of algebraic manipulation. So I hope that was okay. Next question. Okay, use an appropriate substitution to evaluate that. So this one, again, u substitution, but what do we use as a substitution? Well, here the ugly part of the integral is x squared minus 9, the square root x squared minus 9. So if we could get rid of that, that'd be useful. Another sort of idea which I would have immediately looking at this is saying, well, we've got x cubed here, we've got a derivative of x squared here, but the only problem is because it's under the square root, there's not much we can do with it. So let's try and sub out the ugly part of the integral. So square root x squared minus 9. So question 2, we've got the integral of, let me just get the limits right of the integral from root 10 to root 13 of x cubed times the square root of x squared minus 9 dx. Okay, so now we said that we want to sub in u equals square root of x squared minus 9, and so let's do that, and we can rewrite that as x squared minus 9 to the power of 1/2, just to make the differentiation a bit clearer. So we have du by dx is going to be then 1/2 x squared minus 9 to the power of minus 1/2, and then the derivative of the inside, because by chain rule we want to take the derivative of the outside multiplied by the derivative of the inside, is just going to be 2x, and that's going to leave us with 2x over 2 times the square root of x squared minus 9. Okay, so now we've got du on dx. We want to rearrange this for dx so that we can sub it in. So let's flip both sides of a fraction and make dx the subject. So dx, well, the fraction, which we can treat, the derivative which we can treat as a fraction is a better way to say it. 2 times x squared minus 9 under root over 2x. And then making dx the sort of subject, we're going to say 2 times the square root of x squared minus 9, x squared minus 9, or divided by 2x du. Okay, so now we've gotten that, and let's name this integral I again. We've got one more step that we've got to do, which we didn't have to do in the other one, and that was to change the bounds of the integral. Because we're changing or transforming this into the u world, I guess you could say, we're going to have to change the bounds of the integral. So when x equals root 10, x squared is going to be 10, minus 9 is going to be 1, so root that is going to be 1. So the integral is going to turn into integral from 1 to, what happens if we sub in root 13 for x? Well, 13 squared, root 13 squared is just 13, minus 9 is 4, square root of that is just going to be 2. So integral from 1 to 2 of x cubed times the square root of x squared minus 9, and then we change our dx into the thing that we got above, 2 root x squared minus 9 over 2x du. Okay, so that's what we get from there, which we can then simplify out a bit by cancelling the 2's. The 2's cancel here, this 2 and this 2, and this x turns this into an x squared, and then we can combine the x squared minus 9's, so that's going to get 1 over 1 to 2 of x squared times x squared minus 9 du. Yep. Now, because we have still x's in our equation, we're going to have to try and convert that into the u sort of expressions. So we know that u equals to square root of x squared minus 9. So then we know that u squared must then be x squared minus 9. And then u squared plus 9 would be x squared. So now we've got the individual components. We've got the x squared minus 9, which is going to be just u squared. And then this thing is just going to be u squared plus 9. So we can rewrite that integral in terms of u. So integral from 2 to 1 of x squared is just going to be u squared plus 9. And then x squared minus 9 is just going to be u squared du. And then that's not a tricky integral, because all we have to do is expand and then apply power rule. So u to the 4 plus 9u squared du. And that's just going to leave us with u to the 5, u to the 5 over 5 plus 9u cubed over 3 from 2 to 1. And this, just simplifying that 9u cubed over 3, we're going to end up with u to the 5 plus 3u cubed 2 to 1. And if you put in all the limits and you simplify everything down, you should get 136 over 5. Just subbing in the limits and simplifying things. So that shouldn't be too tricky. And that's our answer. 136 over 5. So we could say that the integral equals to 136 over 5. And so we're done. Okay. That was for 3 marks. I mean, there was a bit of work involved, but it wasn't too hard of a 3-marker. And now the other method of, I mean, I guess you could call it algebraic manipulation, is partial fractions decomposition. So that is where you factorize q of x into real and linear quadratic factors, and also like if we have p of x over q of x, and then we evaluate each of those different terms, and then those terms are oftentimes easier to integrate. Okay, and this is how you would do it if you had ax minus b to the power of m, where you had, like, say, a repeated term, or like a term to a power of 2 or 3 or something in the denominator. So have a read through that, but I won't spend too much time on that one because it's just sort of a technicality. It's not that much different. Just have an additional term thrown in there. Okay, so integral of 6 over x squared minus 9. This isn't too difficult of a question, but for 3 marks, that's pretty generous. It's just a bit of work, not too much, considering how nice the question is. So this is our 3rd question, I believe. Yeah, 1, 2, 3. So we've got 6 integral, so question 3, integral 6 over x squared minus 9 dx. Now immediately when you see the difference of 2 squares down the bottom, you want to try and factorize it. So you have x plus 3 times x minus 3 dx. And from there, we go ahead and use our partial fractions decomposition. So that we can say that 6 over x plus 3 times x minus 3 can be rewritten, or is equivalent to, sometimes you'll see 3 lines say equivalent to, a over x plus 3 plus b over x minus 3. And now that means we can multiply through it by x plus 3 times x minus 3. That's going to leave us with 6 times x minus 3 plus b times x plus 3. And now, since it's equivalent to, we can go ahead and sub in values of x so that we can figure out what a and b have to be. And because we can sub in any value of x, it's best to choose convenient values of x, which cancels out some of the terms or most of the terms except for the one that you're interested in. And so in that case, if we let x equal 3, that's going to cancel out the first term. So that's going to be 6 equals a times 0 plus b times 3 plus 3 is 6, so 6b. And that must mean that b equals 1. Okay, so that's b evaluated. Now we've got to evaluate a, so 6 equals a times x plus 3. And we know what b is now, so x minus 3 just by itself there. Sorry, the other way. That should be a plus. That should be a minus, that should be a plus. Yeah. And if we let x equal minus 3. Now that's going to cancel out the second term. We're going to be left with 6 equals a times minus 3 is minus 6. And so that's going to give us minus 6a. And so a equals to minus 1. That's pretty nice because now we can rewrite our expression as 6 over x plus 3, whatever was in the integrand, x minus 3. That we can rewrite as minus 1 over x plus 3 plus 1 over x plus 3. And so then our integral, this integral of 6 over x plus 3 times x minus 3, our original integral, we can rewrite as the integral of minus 1 over x plus 3 plus 1 over x plus 3 sorry, that should be a minus x minus 3 is going to be then the integral minus ln x plus 3 plus ln x minus 3. Because those are just fairly easy ln integrals because the derivative of the bottom is already on the top, and so that's just going to leave us with that. And we've got a plus c because it's an indefinite integral, and so that's going to leave us with ln x minus 3 over x plus 3 plus c, and so we're done. So our integral we've evaluated to be ln x minus 3 over x plus 3 plus c. Okay, so now we can jump to the next question. So that wasn't too bad. It was just a bit of partial fraction decomposition. Just have to be a bit careful with the algebra because there's a lot of terms flying around. This is probably towards the easier end of the partial fractions decomposition because we've got no repeated terms, we've got no quadratics in the denominator and that sort of thing. But if you do, then just have a look at the slides when you get a chance. That sort of covers it. So when you have quadratics, you've got to throw in linear terms as well. But yeah, if the denominator is quadratic, put a linear term in the numerator. If the denominator is linear, put a constant term in the numerator. But yeah, in this case, we just had linear terms, and so we had constant terms in the numerator. Okay, the next type of integration problem that you're going to face in extension 2 is integration by parts. Now, integration parts comes from reversing or just reusing the product rule. So if we've got the derivative of two values, doing a bit of algebraic manipulation will show that the integral of u times v dash dx equals uv minus the integral of vu dash dx. So whenever we have these sort of integrals, we've got to choose which one's going to be u, which one's going to be v dash, and that's an important part of these sort of questions. So yeah, so the way we do that is by using the Lie8 rule. Now this isn't in itself a rule, it's more a rule of thumb. It's just something useful. So to pick which one we want to differentiate, so the u, we want to sort of follow this order. If we've got a log in there, then we want to try and make that RU. If we've got an inverse in there, we want to try and make that RU, and then eventually algebraic, trig, and exponential. We prefer to have, say, exponentials go into our v dash because it's easier to integrate an exponential than it is to integrate, say, something like a log or an inverse trig function, but it's still possible. So this is still just a rule of thumb, but yeah. In this case, in most cases where you've got sort of simpler, direct integration by parts sort of questions, this rule tends to work. And here's an example of that sort of thing. Integral of x times ln x dx. So let's do that one. So we have integral of x times ln x from e to 1. So question 4, integral from 1 to e of x times ln x dx. And we're going to let that equal I just for convenience because we're going to have to use it again. Okay, so using our Lie8 rule, logs, inverse, algebraic, trig, and exponentials, here we've got a log in the in our expression, so we want to try and make that RU because trying to integrate ln x, although it's possible, not terribly difficult, you're going to have to use integration by parts again. So let's try and use that to be our RU. So u is going to be ln x, which then leaves us with v dash equals to x. So then differentiating u, you end up with 1 on x. Integrating v, we end up with x squared on 2. just by integrating x. And then from there, we use just the formula for integration by parts. I mean, I call it a formula, but it's just a rearrangement of the product rule. It's just going to be this one times this one minus the integral of that one times that one. So first we have ln x times x squared on 2, and that's with bounds e to 1, minus the integral of 1 on x times x squared on 2 is just going to leave us with an x on 2, and that's going to still have the bounds e to 1. Okay, so now we see how that's reduced it down to a very easy integral, because that's just going to be a linear term. Integrating a linear term is just going to leave us with a quadratic term, and then that's just a matter of subbing in the bounds, which if you sub in ln of e is just going to be 1, and then that's going to leave us with e squared on 2. And then if you sub in the 1, you'll see that ln of 1 is just going to be 0. So that's going to leave us with minus 0. And then integrating this one, or we'll pull out the half first, just to be safe in terms of the algebra. And so that's going to leave us with e squared on 2 minus 1/2 times x squared on 2 from e to 1. And from there, we see that we've got e squared on 2 minus, and I'll pull out the half here, so that's going to leave us with a 1/4. That's going to be e squared minus 1. So that's going to give us e squared on 2 minus e squared on 4 plus 1/4. And 1/2 minus 1/4 for the e squareds is just going to be 1/4. So that's going to leave us with an e squared on 4 plus 1/4. And so we've integrated that by parts. So then the integral must be equal to e squared on 4 plus 1/4. And so we're done. Okay, so that wasn't too bad of a question. For 3 marks, there's one of the nicer integration by parts question. I just did that to demonstrate the concept. But where integration by parts comes in to be towards the harder end of the spectrum of questions is when you end up with recurrence relationships, which is the next question. Okay, so there are 2 methods that you would use to derive these recurrence relationships. Like I said, one is integration by parts, and the second one is by using the add, subtract, and multiply, divide trick. But more often than not, you're going to have to use integration by parts. Some we may have to use substitution, but definitely integration by parts is probably the one that turns up most common. Okay, so here's one. In equals integral from 0 to -3, x to the n square root of x plus 3 for n between 0 and from 0 onwards. Okay, so let's do that one. So this is question 5 of the integration set, I believe. So in equals integral from 0 to -3, x to the n root x plus 3 dx. Okay, so now we want to try and derive a reduction formula for it. Because we want to try and derive a reduction formula for it, if we go back to the question, we see that we've got an in minus 1. So if we want to have an in minus 1, that means that we're going to try and bring down the power of x to the n. So if we try to integrate x to the n, that's going to bring up the power. But if we try to differentiate it, that's going to bring down the power. So that's a good sign that we're going to have to put u as being our x to the n, so that when we differentiate it, that's going to be n times x to the n minus 1 to bringing down the power. And then v dash is just going to be square root of x plus 3, or x plus 3 to the power of 1/2. Integrating x plus 3 to the power of 1/2 is just going to leave us with x plus 3 to the power of 3 on 2 multiplied by 2 on 3. Just by power rule or like chain rule, but in this case, because we've got a linear term in the within the brackets, that's going to leave us with a 1 outside because the derivative of x plus 3 is just 1. Okay, now using integration by parts, that's going to leave us with x to the n, 2/3, x to the n, x plus 3 from 3 to the power of 3 on 2. And the bounds of that is the same as that for the integral, so 0 to -3 minus n times the integral of 2/3 x to the n minus 1. I just pulled out the n for convenience, times x plus 3 to the power of 3 on 2 dx. And when we sub in the limits here, we see that when we put in the 0, that's going to make this entire thing 0 because 0 to the power of n is still 0. And then minus 3, when we put that in, that's going to make this term 0, so make the entire thing 0. So this sort of n term here is just all going to go to 0. So that just leaves us with the integral minus 2n over 3, integral from x to the n minus 1, n minus 1, to x plus 3 to the power of 3 on 2. dx. Now, when we have a look at this integral, we see that we're very close to the original integral, like in minus 1, but we've got this power of 3 on 2 instead of power of 1/2. So let's try and see if we can manipulate this so we can get a power of 1/2 by itself. So what I'm gonna do is just pull out a factor of 1 and then split that into an x plus 3. So split the 3 on 2 into a power of 1 and then a power of 1/2. And then expanding that, so 0 to negative 3, 0 to negative 3, 0 to negative 3. Make sure you don't forget the bounds of the integral like I did there. So then when we expand that, we're going to end up with x to the n plus 3 times x to the n minus 1, and then times that by root x plus 3 dx. I just expanded the x to the n minus 1 into the x plus 3 term. Okay, so once we've gotten that, we can go ahead and just expand out the root x plus 3 to give integral from negative 3 to 0 of, sorry, the balance should be that way, so 0, negative 3, 0, negative 3, and that should be a 0 to negative 3. Okay, so then we've got x to the n root x plus 3 plus 3 times x to the n minus 1 root x plus 3 dx. So here, when we look at this integral, we can split that into integral from 0 to negative 3 of x to the n root x plus 3 dx. And I'll show you why I did that in a second, or if it's become obvious, then congratulations, well, good job, because that means that you're sort of developing insight into, or foresight, mathematical foresight on this. So yeah, make sure, and that's just something that comes with practice. So root x plus 3 dx. And the 3's and the over 3 here, the 2n over 3, and this 3 here cancel to just leave a negative 2n. And that means that when we have this integral here, this one is just the same as saying in. And this integral here is just the same as saying in minus 1. And so we can rewrite our in, our original integral, as negative 2n over 3 in minus 2n in minus 1. And because we want in minus 1 by itself on the right hand side, if you go back to what we wanted to prove, we'll bring all the in's together on the other side, so we end up with in times 1 plus 2n over 3, just bringing it onto the other side, equals minus 2n, sorry, there should be an n there, minus 2n in minus 1, so that's equal to minus 2n in minus 1. And so if we combine the fractions here, that's going to give us in times 3 plus 2n over 3 equals negative 2n in minus 1. And then just bringing everything, all the other fraction stuff onto the right hand side, that's going to give us in equals negative 2n times 3 is just going to be negative 6n over 3 plus 2n in minus 1. And so we're done. We've proven that we've proven the reduction formula, in equals minus 6n, 3 plus 2n, in minus 1. Okay, and so that's that. Question 2. We want to find the value of I2. Because we want to find the value of I2, that's just a matter of using our reduction formula now. We've just derived it, so let's go ahead and use it. So I2 I2 is going to be something like negative 12 over 3 plus 4 is 7, I1, right? Negative 12 over 7, I1, and I1 still isn't that easy to integrate. And our reduction formula is also defined further than I1, so we can go ahead and reuse the reduction formula again to simplify I1. So in this case, n equals 1 now, so minus 6 over 3 plus 2 is 5. So I0, we bring that down by 1, and that leaves us with 12 times 6 is 72 over 35, and the negatives cancel, and we're left with just the integral from 0 to negative 3, x to the 0, root x plus 3, dx. Now that's not too difficult to integrate because x to the 0 is just 1, so we're left with 72 over 35, integral from 0 to negative 3 of root x plus 3, dx. And that's just a matter of applying chain rule, so we can rewrite x plus 3 to the power of, root x plus 3 as x plus 3 to the power of 1/2. So then it's just reverse chain rule, and it's going to leave us with 72 over 35 times 2/3 x plus 3 to the power of 3 on 2, just by reverse chain rule, and we're left with 0 and minus 3 as the bounds. If we sub in 0, we see that we end up with 2/3, 72 over 35 times 2/3 of 3 to the power of 3 on 2. And then if we sub in minus 3, that's going to leave us with 0, so we don't have to include that term. And so we have 72 over 35. And 3 times the 3 on 2 divided by 3 is just going to leave us with a 2 times root 3. So it's times 2 times root 3. So that's just going to be 144 root 3 over 35. And so we're done. So I2, that was what we were working out, is 144 root 3 over 35. So yeah, that's how you would use a reduction formula once you've derived it. So yeah, that wasn't too bad, but it did involve a bit of work for 2 marks. Yeah, it's just a matter of being careful with your numbers and your algebra as you're going through. And even if you're not able to completely get the reduction formula in part 1, for example, in an exam, still feel free to do part 2, because sometimes when they've given you the reduction formula, you feel free to use it even if you haven't completely shown it in the part 1. Obviously try your best to show it and try and put down as much working as you can, just so even because partial marks is a thing. And so yeah, I do. Okay, now we've got a new topic, is proof. And so in extension 2, there's a range of methods which we can use to prove things. So there's direct proof, there's proof by mathematical induction, there's proof by contradiction, proof by contrapositive, and inequality proofs. Now, with mathematical induction, you would have seen it in extension 1 already, but extension 2 just takes it further to consider a broader range of questions or broader range of things that you can prove using mathematical induction. Okay, so it's also important to be familiar with the mathematical notation involved in proofs. So when you've got for all symbols and belongs to and there exists, make sure that you're familiar with this sort of thing. So here's an example. Determine which of the following quantified statements are true. So for all x but 1 belonging to reals, there exists x2 belonging to real such that x2 is greater than x1. Now what does that mean? Well, that just means that for any x1, I pick any x1, is there an x2, or there exists an x2 such that x2 is greater than x1. So if I give you any number, are you able to give a number which is bigger than that? Well, the answer to that is true, right? Because if I gave you 10, you could give me 11, right? If I gave you 20, you could give me 21. So that's fine. But what if we look at question 2? There exists x1 belonging to reals such that for all x2 belonging to reals, x2 is greater than x1. So if I give you any value of x2, are you able to come up with a value of x1 which is greater than all of that? Well, the answer is false, right? Because there is no such thing as the biggest number. Okay, so For proofs involving divisibility, it is often useful to express values in terms of the factor in consideration. So if a and b belongs to integers, so remember z means integers, and b is divisible by a, then there exists m belonging to the integers such that b equals an. So just another fancy way of saying that if we can divide b by a, then that means that we can multiply a by some number to give you b, and that number has to be an integer. Okay, so here's an example question that uses a whole bunch of the terminology and sort of a direct proof method and even a proof by contradiction, but I'll show you that as we go through it. Okay, so we've got prove that proposition P is true. If k plus 1 is divisible by 3, then k cubed plus 1 is divisible by 3. Okay, how do we do that? Well, with divisibility proofs, remember when we want to prove that something's divisible by something else, we want to see if we can pull out a factor of that something. So in this case, we want to show it's divisible by 3. So in the end result, we want to show that our final result is divisible by 3. But what are we given to start off with? Well, if we go back to the question, one second, if we have, so if we go back to the question, we have k plus 1 is divisible by 3. That's what we know. And then we want to prove that if that's true, that if k plus 1 is divisible by 3, then k cubed plus 1 is divisible by 3. So we know that k plus 1 is divisible by 3. So what does that mean? Well, it means that we can write k plus 1 as 3j, where j is some integer, because k plus 1 is divisible by 3. So then k cubed plus 1, right? Well, that, if by the sum of two cubes factorization is equal to k plus 1, k plus 1 times k squared minus k plus 1. So again, sum of two cubes terms up, so make sure you're familiar with it. And we know that k plus 1 is divisible by 3, so we can leave that, or substitute in 3j and leave the k squared minus k plus 1 as it is. And that means that 3 is a factor which we can pull out of this entire thing, j times k squared minus k plus 1. And so because we can pull out 3 like that, that means, and we know that j times k squared minus k plus 1, that also belongs to the set of integers, right? So that means that, I'll make a note that clearly j times k squared minus k plus 1 belongs to the set of integers, and so that means that k cubed plus 1 is also divisible by 3, because we can pull out a factor of 3. Divisible by 3, and so on. Okay, so that was part 1. Part 2 asks us something interesting in terms of, it's just a 1 marker, where it's asked for the contrapositive of that statement. It hasn't asked us to prove anything or do anything with the contrapositive. It just says, write down the contrapositive of the proposition P. If k plus 1 is divisible by 3, then k cubed plus 1 is divisible by 3. If we have a statement P implies Q, if P then Q, then the contrapositive is the same as saying if it's not Q, then it's not P. So in this case, if it's not divisible by k cubed plus 1, then k plus 1 is not divisible by 3. So that's our contrapositive. Because in this case, P is the statement if k plus 1 is divisible by 3. Q is the statement k cubed plus 1 is divisible by 3. So not Q would be the k cubed plus 1 not being divisible by 3. And not P would be k plus 1 not being divisible by 3. So k cubed plus 1 is not divisible by 3 if k cubed plus 1 is not divisible by 3, k plus 1 is not divisible by 3. That's the contrapositive. Divisible by 3. And so we're done. Part 2. Done. Part 3. Okay. Part 3 says, write down the converse of the proposition P and state with reasons whether the converse is true or false. Okay, so the converse, remember, is where it goes not P and not Q. Well, the converse then would be the that's the converse, sorry, would be when it's reversed, my mistake. So if k cubed plus 1 is divisible by 3, then k plus 1 is divisible by 3. That's what we want to prove. So we first write down the converse. So the converse looks something like this. If k cubed plus 1 is divisible by 3, then k plus 1 is divisible by 3. So that's the converse. So just flipping the P and Q of that statement. Okay, and now we want to try and prove that. And the way we prove that, now there are different ways about going about it, but I think the nicest way is to use proof by contradiction. We'll come to a more detailed version, sort of a discussion of proof by contradiction, but here we're just going to assume that the statement is false, right? So assume k plus 1 is not divisible by 3. So we assume that k cubed plus 1 is divisible by 3, but the k plus 1 is not. Okay, and that's going to mean that k cubed plus 1, which we're going to use again as a difference of two cubes factorization. K plus 1 times k squared minus k plus 1. We said that k plus 1 is not divisible by 3, so that means that there has to be a factor of 3 in this thing. Because if this thing is divisible by 3, then the right-hand side also has to be divisible by 3, so this thing must be divisible by 3. Okay, so if that's divisible by 3, then we can say that k squared minus k plus 1 equals 3m, where m is a different number now, belonging to the set of integers. That has to be equal to 3m because it's divisible by 3. Now here's a little clever trick that I'm going to use, and you'll see why we're going to use that in a second. So if we rewrite this minus k term as being plus 2k, and we're going to leave everything else as it is, and we're going to make it minus 3k, that's going to be equal to 3m. Now why is that helpful? Because when we have k squared plus 2k plus 1, that means that we can factorize that as k plus 1 squared minus 3k, and that's equal to 3m. So because this thing is divisible by 3, right, that means that this thing also has to have a factor of 3, which we can pull out, because then only we can have both sides divisible by 3. So because we've got a factor of 3 we can pull out of here, there has to be a factor of 3 which we can pull out of here. So this implies that k plus 1 squared must be divisible by 3. So that means that k plus 1 must be divisible by 3. Right? And because we know that k plus 1 must be divisible by 3, that's a contradiction to our original assumption. So we're going to say contradiction. So then our original assumption must be false. So the original assumption is false. And so we've pretty much proven what we need to prove. So because the negation is false, the original statement must be true. So if k cubed plus 1 is divisible by 3, then k plus 1 is divisible by 3. I would just usually write that as a conclusion in the end. Okay. Now so here's the contrapositive again. In some cases, when you've got proof of the original, which sometimes may be a bit tricky, considering the contrapositive may simplify things and might be an easier statement to prove. So for example, prove that if n cubed minus 13 is odd, then n is even. Now proving that directly without having to use the contrapositive is a bit tricky. So then the better way to do it is to consider the contrapositive. And what would the contrapositive of this statement be? Well, if this is p, this n cubed minus 13 is odd, that's p, and this n is even thing, that's q, then that must mean that not q implies not p must be if n is odd, then n cubed minus 13 is even. That's the contrapositive. So the contrapositive is that n is odd and n cubed minus 13 is even. If we can prove that, then we're done. So the way we do that is pretty easy in the sense that n cubed minus 13, because n equals 2k plus 1 for some k belong to the integers, because n is odd, we just substitute that in for n cubed and then expand that out, and then from that we see that we can actually pull out a factor of 2, and that makes n cubed minus 13 even. So the contrapositive is true. We've proven that the contrapositive is true, so that must make the original statement also true. Okay, proof by contradiction, which we did use before, essentially utilizes a fundamental property of the negation of a statement. If the original statement is true, a statement is true if and only if its negation is false. So it works both ways. Remember, if and only if, so you can go this way in the implies, and we can go this way in the implies. So a statement is true if its negation is false, and if its negation is false, a statement is true. So if we can show that the negation is false, then we've proven that the negation is true. Sorry, that the original statement is true. And a very common example for that is the proving something is irrational sort of cases, where, for example, the classic example is root 2, prove that root 2 is irrational, or root 5 is irrational, or something like that. But here we've got something, we've got log base n of n plus 1 is irrational. We want to try and prove that. Okay, so the way we do that is very similar to how we would do the root 2 case. So we start off by supposing, so this is question 3, suppose log base n of n plus 1 is rational. So proof by contradiction, you assume the negation of the statement. So log base n of n plus 1 is rational. Well, what does that mean to be rational? Well, it means that we can rewrite this thing as being equal to p on q, where p and q belong to a set of integers, and an additional condition is that q cannot be equal to 0, because if it's equal to 0, then that's no longer defined. Now, if we want to try and now we want to try and manipulate it to show a contradiction. So let's try and take both sides to the power of n to get rid of the log. So that's going to take n. That's going to leave us with n plus 1 equals n to the power of p on q. And then from there we can take both sides to the power of q, and that's going to leave us with n plus 1 to the power of q equals n to the power of p. Okay, now this next step is a bit tricky to see, but it comes with a bit of experimentation. If you actually sum in numbers for n, you'll see that this is a contradiction. And here's why. If n is even, right? If n is even, then the left-hand side, because we've got an even number plus 1, that's going to be an odd number. And it doesn't matter how many times you multiply an odd number by another odd number, that's going to leave an odd number, right? By itself. So left-hand side is going to be odd. And the right-hand side, because n is even, and we've got an even number multiplied by an even number over and over again, that's also going to be even. And because the left-hand side is odd, but the right-hand side is even, that's a contradiction. So we've found a contradiction if n is even. So what happens if n is odd? Coming back to the expression, we see that we've got, if we got an odd value of n, an odd number plus 1 is going to give us an even number, so then the left-hand side will then be even, and the right-hand side, just an odd number multiplied by itself over and over again, is just going to leave an odd number. So the left-hand side is going to be even. Right, and the right-hand side is going to be odd. So that's going to lead to another contradiction. So we've proven whether, even if n is even or odd, contradiction. Okay, let's spell that. Yep, I think that's right. So yeah, we've proven that even if n is even or even if n is odd, it's going to lead to contradiction. So that means that we've got an overall, since both cases result in contradiction, that must mean that the original assumption is false. Because you can't have anything that's not odd or even, right? So original assumption is false. We've covered every possible case. So original assumption is false. And so that must mean that log base n of n plus 1 is irrational for n belonging to z and n greater than 1. Okay, so we're done with that now. Okay. So not too bad for 3 marks. Didn't involve a bit of work, but main thing was seeing the odd and even sort of conclusions. That was probably the trickiest part of that question. Okay, now the other type of proof that could turn up are inequality proofs. And inequality proofs pretty much involve, inequality proofs pretty much involve using these properties and workings of inequalities to prove what we need to prove. And 2 very common inequalities that you're going to have to use and manipulate further to produce what you need in the end is going to be your AMGM inequality, that's this one here. So make sure that you know how to prove that. It's not too difficult to prove, just make sure you are familiar with how to prove that. And then your triangle inequality, which is a bit trickier to prove, but make sure you understand why or how it works, even geometrically. Okay, here's another inequality proof, but this one, with this one, I want to demonstrate a very important aspect of inequality proofs, a very important way of approaching inequality proofs. So this is question number 5, I believe. Let's just double check that it is. 4. Okay, so question 4. X times y minus x plus 1 is greater than or equal to y. That's what we want to prove. The thing that I want to demonstrate is that quite often with inequality proofs, if you're working backwards, right, start from the thing that you want to prove, work backwards until you can find something that's easy or like a well-known fact of this about this statement. Working backwards and then rewriting the proof the other way around always, or not always, but helps or works a lot of the time. So we have xy minus x squared plus x is greater than or equal to y, just expanding the brackets and bringing everything onto one side. We have that minus y is greater than or equal to 0. Now we have a x minus y here and a y minus x squared here. So what happens if we pull out a factor of x? We're going to end up with a y minus x. And because we want another y minus x, I'm going to make that negative. And that's going to leave us with y minus x here is greater than or equal to 0. And from there, we can pull out a factor of x minus 1 and a y minus x, so that get that equal greater than or equal to 0. So when we look at this statement, we go, well, is this easy to prove? In order to verify whether it is easy to prove, have a look at what they've said. They've said that x is greater than or equal to 1. So if x is greater than or equal to 1, that must mean that, so we've said that x is greater than or equal to 1. That must mean that x minus 1 is greater than or equal to 0. So that's going to be positive. And if they've also said that y is greater than or equal to x. So that must mean y is bigger than x, so y minus x has to be positive. Because when you take a bigger number, when you take a smaller number away from a bigger number, that's going to be positive. So if you have 2 positive numbers multiplied together, obviously that's going to be positive. So then your starting line for this proof should be that since x is greater than or equal to 1, x minus 1 has to be greater than or equal to 0. And since y is greater than or equal to x, y minus x has to be greater than or equal to 0. So then using those 2 facts, this one and this one, you can go ahead and multiply it out. So so all this would be, everything here, above the here, is just scrap working, right? That's not your actual proof. That's just working that you did on the site. That shouldn't be something that, yeah, okay, so that's just your working, or your thought process. And then you got x minus 1 times y minus x is greater than or equal to 0, because when you multiply 2 positive numbers, it's going to be positive. And then from there, just expand and work backwards to what you had originally. So your proof would look something like this. So we observe that x is greater than or equal to 1, so x minus 1 has to be greater than or equal to 0, y is greater than or equal to x, so y minus x has to be greater than or equal to 0, just multiplying those two out, and then working backwards to what we had originally, we're done with the proof. So yeah, working backwards oftentimes does help with these sort of questions. Okay, so here's the AMGM sort of inequality question. We're gonna have to use the AMGM inequality, so let's quickly give that a go. Yeah, so first they've said to prove that a squared, the 2ab is less than or equal to a squared plus b squared. So that's a fairly standard, 2ab is less than or equal to a squared plus b squared. That's your fairly standard AMGM inequality, and the way you do that is just by starting with a minus b squared, because whenever you square something, it's going to be positive. That's going to be greater than or equal to 0. Because it's greater than or equal to 0, that must mean that a squared minus b squared minus 2ab has to be greater than or equal to 0. Sorry, my mistake. A squared plus b squared minus 2ab has to be greater than or equal to 0. So a squared plus b squared has to be greater than or equal to 2ab. And we're done. That's the AMGM inequality. Now the next step, now that's probably maybe worth 1 mark potentially. The next step is to use that to prove this statement here. 3 times AB plus BC plus CA is less than or equal to A plus B plus C squared. So 3 times AB plus BC plus CA is less than or equal to A plus B plus C squared. Okay, so because we've got that, this AB plus BC plus CA, that looks a bit like our 2AB term. So let's see what happens when we try and come up with that term for BC and CA. So we've got the AB term, so we've got 2AB is less than or equal to A squared plus B squared. Similarly, 2BC is less than or equal to B squared plus C squared, and then 2AC is less than or equal to, or CA or AC, is going to be equal to A squared plus C squared. So what happens if we go ahead and sum all those inequalities together? That's going to leave us with 2AB plus 2BC plus 2AC is less than or equal to, because we've got 2B squareds and 2A squareds and 2C squareds, we can say that's going to be less than or equal to 2A squareds plus 2B squareds plus 2C squareds, and then we can divide through by 2. So that's going to leave us with AB plus BC plus AC is less than or equal to A squared plus B squared plus C squared. Right? Now, that's useful because we've got everything in the brackets there. And as a side note, or like as part of this proof, we're going to have to observe that A plus B plus C, right? That squared, what would we get when we square that? Well, that's just going to be equal to A squared plus B squared plus C squared plus 2AB plus AC plus BC. Now, whenever you see these sort of terms like this, AB plus BC plus AC, you have to remember that that's something that turns up quite often when you're expanding these sort of things, right? When you've got expanding A plus B plus C squared, when you're expanding all that, that sort of thing turns up quite often. So that's going to be A squared plus B squared. Oh, we've already got that. And so that 2AB plus AC plus BC, we said that that has to be less than or equal to A squared plus B squared plus C squared, right? And so this A squared plus B squared plus C squared, because it's greater than that, we can say that this thing is going to be greater than or equal to AB plus BC plus AC. We've just replaced this with this, with this. Because we know that that A squared plus B squared plus C squared thing is bigger than that AB plus BC plus AC thing. So then we leave this alone, we leave it as it is. And then we see, okay, we've got two of these guys plus one of these guys. That's going to make 3 of these guys, so 3AB plus BC plus AC, right? And so we've proven that A plus B plus C squared, A plus B plus C squared is greater than or equal to 3 times AB plus BC plus AC. And so we're done. Now, the question might be, where did the idea come from to consider the a plus b plus c squared? Now, the logic behind this step here, where we're adding each of the AMGM inequalities together, should make sense in the sense that we've got AB and BC and AC terms, and that's what we would get from the AMGM sort of cases. But the idea to expand this comes from just practice, honestly. Being able to observe what we would get with a plus b plus c, and sometimes experimentation. Just experiment with the question a bit, and then you'll be able to see that this expansion is what you would get when you expand this. And when you see this expansion here, you should be like, oh, okay, I saw that before, that was here, and so we're going to put that all together. And that's going to leave us with this. So yeah, it's definitely something that comes with practice. So practice, 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 like I always say, but feel free to experiment. Make sure that in an exam, obviously keep track of the time, but if you've got time, make sure that you do experiment with the question. Okay, here's another one, an inequality proof with induction, and I just did this so we can briefly demonstrate how you can combine different forms of proof. So what do we do for mathematical induction for the first step? Well, that is to consider the base case. So usually in extension 1, our base case would be when n equals 1, for example. In this case, n is defined for n greater than or equal to 11. This inequality holds. We want to show that that's true. So our base case would then be 11, right? So because our base case is 11, we're going to sub that in. So when n equals 11, our left-hand side equals 11 squared, that's equal to 121. And our right-hand side is just going to be 9 times 11 plus 13, because that's 9n plus 13, and that's going to be equal to 112. And clearly, the 112 is less than the left-hand side, and so the statement is true for n equals 1. And then our next step is to assume true for n equals k. So that is for some value of k, n equals k, and k is greater than or equal to 1. Greater than or equal to 11. The inequality holds. K squared is greater than 9k plus 13, and we wish to prove that the statement holds for n equals k plus 1, and that's what we want to try and do. So we want to prove this statement here. So when we consider k plus 1 squared, when we expand that way, we're going to end up with k squared plus 2k plus 1. So we saw that this k squared plus 2k, we saw that k squared is greater than 9k plus 13. So we can replace that k squared with a 9k plus 13 here, and then that leaves us with a 2k plus 1. Now, that is the same as saying 9k plus 22 plus 2k minus 8, because the 9k and the 2k stay the same, but the 22 minus 8, that's 14, and 13 plus 1, that's 14. And the reason we do this, right, this is the tricky bit. The reason we do that is so that we can manipulate it to the end goal. So, because k is greater than or equal to 11, 2k is greater than or equal to 22. So 2k minus 8 has to be greater than or equal to 14. And that's why we replaced that 14, that 13 plus 1 being 14, that 13 plus 1 being 14, we replaced that with a 2k minus 8, because 2k minus 8 has to be greater than or equal to 1, so we can guarantee that 9k plus 22 plus, 9k plus 22 plus 14 is less than or equal to whatever was above it. And now, if we get rid of that 14 term, that's going to just leave us with 9k plus 22, which is obviously going to be smaller than the adding 14 term, so then we're done. K plus 1 squared is greater than 9k plus 22. Now this required this step here, which was probably the trickiest step, but again, feel free to experiment with your original assumption, like was what they've given you, that k is greater than or equal to 11, and in that case, because we've got this 2k here, and 2k minus 8, because we can replace that with a 14, that greatly simplifies things, because getting rid of 14, we know that that's going to be bigger than 9k plus 22. And so by induction, it holds for all integers n greater than or equal to 11. Okay, now for some vectors. Now with vectors, so we've got vector from Despicable Me. Okay, so with vectors, in Mathematics Extension 1, vectors is definitely something you would have talked about, and it's definitely something that you would have played around a bit with. But in Extension 2, all the concepts and the topics and so the rules for vectors, all of them still hold. It's just we've got an extra dimension added on. So the parallelogram law for addition, just how you manipulate vectors, how you deal with them, all of that stuff still holds. It's just we've added in another dimension, and that's quite natural because we live in a 3D space, right? Okay, so in addition to that, we've also got equations of lines. So just as a side note, whenever we've got a line, we've got r equals a plus lambda b. A is just some vector or to a point on that line, and b is just some vector parallel to that line. So yeah, make sure you're familiar with that. So we've got two lines given by -2, 1, 3 plus lambda times 1, 0, 2 plus and r2, 4 minus 2q plus mu times p3 minus 1. And we want to show that these lines intersect and that they're perpendicular. And we want to show, we were given that they intersect and that they're perpendicular, and so we want to find the values of p and q. Okay, so the way we do that is, if we come back to the question, we know that if they're perpendicular, then the dot product of this vector, this 1, 0, 2, with p3 minus 1 has to be equal to 0. And why is that? Well, because these two vectors are parallel to the lines, then the dot product between them should give us information about the angle between the lines. So on to some vectors now. So 1, 0, 2, so because they're perpendicular, so since perpendicular, the 1, 0, 2 vector from line 1 dotted with the p3 minus 1 vector, p3 minus 1 vector from the second line should be equal to 0. So then just expanding that out gives us p, 3 times 0 is 0, minus 2 has to be equal to 0, so therefore p equals 2. Okay, so that was pretty easy to find p, and then now we've got to find q, and we're going to use the second property that they've given us, is that the lines intersect. And since I'm going to call the first one L1, since L1 and L2 intersect, their coordinates, or like the vectors, have to be equal at some point for some lambda and mu values along the span, right? They have to be equal. So that means that minus, just coming back to the question, minus 2 plus lambda, right, has to be equal to 4 plus mu times p. Just equating components. When you equate components, you'll see that you come up with three equations. Minus 2 plus lambda equals 4 plus 2 mu. And then 1 equals to minus 2 plus 3 mu. And then 3 plus 2 lambda equals q minus mu. And those are your three equations that you would get when you just equate components. Now, from this, the second equation is probably the easiest to solve because we can directly solve for mu from that equation. So bringing the 2 onto the other side, we end up with 3 equals 3 times mu. So mu equals to 1. And because mu equals to 1, we can use that to solve the first equation, solve for lambda. So minus 2 plus lambda equals to 4 plus 2 times mu. So since mu is just 1, that's just going to give us with 4 plus 2. So lambda equals 6 plus 2. So that's just 8. And because we've got lambda and mu now, we can sub that back into our third equation. And that's going to give us 3 plus 2 times 8 equals q minus mu is 1. So 2 times 8, well, that's just 16. 16 plus 3 is 19. So q minus 1. So that's going to leave us with q equals to 1 plus 19, or 20. So therefore, p equals 2, and q equals 20. Okay, so not too difficult. For 3 marks, for the amount of work that we did, I think it's probably pretty reasonable considering the equations weren't terribly hard to solve. So yeah, 3 marks, that's pretty generous. Here's a vector proof question, and now with vector proofs, it's very similar to the type of proofs that you would see in Extension 1, particularly because a lot of questions, proving things in 3D is a bit tricky, but the concepts are still the same. But what I would recommend is make sure that you're familiar with all your properties for shapes and quadrilaterals and all that sort of stuff, just because that could come in useful when you're proving things. So for example, if you want to prove something is a parallelogram, what does it mean to be a parallelogram? Right? Make sure that you're familiar with all those sort of things. So here we've got a triangle ABC, and assume, as per the classic sine rule and cosine rule conventions, that A equals angle BAC, B equals angle ABC, and C equals angle ACB. And we want to prove that, we want to prove that AB equals AC cos A plus BC cos B. Now, whenever you see causes turn up, that's a good sign that we're probably going to have to use dot product, which in this case, we are going to end up having to. So let's first draw a diagram of the question. Most questions tend to come with diagrams, but in this one it doesn't, so let's do it. What it means by just the general sine rule and cosine rule conventions is that if this was triangle ABC, this angle in here would be angle A, this angle in here would be angle C, this angle in here would be angle B. And yeah, that would mean that, so that would mean that first thing that we want to do is try and come up with an expression for AB, right? Or try and come up with expressions that use AB. So what happens when we dot AB with vector AC? Well, that's just going to be the length of AB just by dot product formula. That's going to be length of AB times the length of AC, cosine of the angle A. Right? And AB dot with AC is that. And what happens if we do AB dot with CB, the other side? If you redraw the triangle, you see that the angle between them is still going to be B. So it's going to be AB times CB lengths cos B. So here's the trick here. So we've dotted like the sides between each other, and then now what we want to do is sum these two expressions. Now that might seem a bit weird or as to why we do that, but here's what comes out of that, and that's what makes it quite useful. So when we sum those two expressions, we're going to have length of AB times length of AC, cosine of the angle A, plus AB times the length of CB, cosine of the angle B. And from there, we can pull out a factor of AB on this side. And that's going to leave us with AC, just because dot products follow the distributive property. So AB dot with AC plus CB. And then we can pull out a factor of AB on this side. And that's going to leave us with length of AC cos A plus length of CB cos B. Now we're almost there in terms of what we want to prove, but we've just got this extra AB term. So we've got to do something about that. But when we look at this triangle, AC plus CB, what does that mean geometrically? And oftentimes that's what you have to do when you get sort of stuck with an expression, is that AC plus CB is just going to be this vector plus this vector, which is just going to be a vector AB. Because that's just going to be a vector AB, we can replace that to leave us with AB dot with AB, which is just going to be AB squared, is equals the length of AB times the length of AC, cosine of the angle theta A, plus CB times cosine of the angle B. And then we can divide through by length of AB, because that's just a scalar now, because the length of AB is just a number. So length of AB equals to AC cos A plus length of CB cos B. Now, we can go ahead and drop the absolute value signs and just drop the vector notation, because when we're just saying AB, usually that just means the length of the side. And so we've pretty much proven what we need to prove. So AB equals AC cos A and times CB cos B. And so we're done. Okay, so that wasn't a terribly hard question, but it just came down to the intuition behind adding those two things. And that comes from the fact that when you add these two vectors, you can sort of interpret them geometrically, particularly with closed quadrilaterals. When you add things, they tend to be nice points on that quadrilateral, and so that simplifies things. Okay, final topic for today before we move on to some exam advice is going to be some mechanics. We don't have an awful lot of time in front of us, so maybe I'll jump through a bit. So here we've got a box, and this is more so a vectors question than a mechanics question as such. Like, it's not a terribly difficult mechanics question. It's just something that involves a bit of resolution vectors. It's definitely something that you would have come across if you did physics in year 11 and year 12. So let's move on to some mechanics then. So question 5A. Yep, so we've got, sorry, that should be question 1 of mechanics. Yep, so we've got 50 kilogram box is initially at rest. The box is pulled along the ground with a force of 200 newtons at an angle of 30 degrees to the horizontal. So there's quite a bit of text involved to this question. But the first part says, by resolving the forces vertically, show that R equals 400. Okay, so to do that, what does it mean to resolve forces vertically? Well, that just means to consider all the forces acting vertically. So vertically, we've got the reaction force, coming back to the diagram, we've got the reaction force R, right, acting vertically upwards, pointing it upwards, so we're going to make that positive. And then we've got a component of this 200 force, the vertical component of that, which is going to be 200 sine 30, minus mg, because that's going to be acting downwards, the weight force acting downwards. That's equal to mass times acceleration vertically. But clearly, because the box is being pulled along the ground, there's no vertical direction acceleration. So that's going to be equal to 0, because ay is 0. So r plus 200 times sine of 30 is just going to be 100, minus mg is just 50g, that's equal to 0. So because we want r to be the subject, we're going to rearrange for that. So 50 times g minus 100 equals r, and 50 times g is just going to be 10, as they've given in the question, right? They said take the acceleration g due to gravity to be 10, so we're going to end up with 50 times 10 minus 100, so 500 minus 100 is going to be 400, and our unit for force in this case is going to be newtons. That's what they gave it to us in, so R equals 400 newtons, and so on. Okay, show that the net force horizontally is approximately 53.2 newtons, is what the second part says. Because we've already resolved the forces vertically, and now it's just a matter of resolving the forces horizontally. So in the positive direction, we've got a 200 cos 30 force. That's just the horizontal component of that 200 Newton force. And then we've got a minus 0.3 R, and that's going to be equal to mass times acceleration in the x direction. Right? So 200 cos 30, that's just going to be 100 root 3. 100 root 3. And then this R value, we already solved for that back in question 1. So 0.3 times 400, that's going to be equal to the mass of the object they've said was 50 kilograms just from the question, right? And that's going to be equal to AX. So the net force horizontally, if we just take this side, that's going to be the net force horizontally equals to, that's going to be approximately 53.2 newtons. So horizontal, if you put that in your calculator, that's what you get. So horizontally, net force is approximately 53.2 newtons. Okay. And then it says find the velocity of the box after the first 3 seconds. That's not too difficult because here the acceleration is constant. So 53.2 divided by 50 is going to give us the acceleration of approximately 1.064, and that's going to be equal to acceleration. And because it's linear and it's initially started at rest, the velocity is going to be just equal to 1.604 times t. So when t equals to 3 seconds, velocity equals to 1.604 times 3, which is approximately 3.192 meters per second. And so we're done. Okay. Now, next question. Next section. that was just resolving forces. That's more so a vectors question than it is a mechanics question as such, because it's just not an application of vectors questions where we're going to have to resolve forces. And part 3, where we're trying to find the velocity, the integration is quite easy because it's a constant value. The equations of motion for a simple harmonic motion in most general form, where it's shifted, the center of motion is shifted by c units, is that x equals a cos nt plus alpha plus c. So if anything tells you to prove that the motion is simple harmonic, if you can show that the motion satisfies this equation here, this x double dot equals minus n squared x minus c, then we're done, right? Because that's sort of like the equation of simple harmonic motion. Here's an example where we're trying to model something with simple harmonic motion. Okay, so I think, yeah, okay. So I think we can quickly cover this one. So we have question 2. It's eventually going to ask for the resultant force on the piston, but because we know that x double dot equals that, if we can find the value of x double dot, then we can find the value of the force because F equals ma, right? We just have to multiply by the mass. Okay, and so in order to do that, we're going to model that equation by finding the different components. So if we go back to this equation, we need the c component and we need the n squared component. So the period of the motion, they've said, was, it says it's completed 40 cycles per second. So that means that t equals to 1 on 40. And that's going to be equal to 2 pi on n, just by property of simple harmonic motion, or like just by property of sines and cosines and transformations of that. So that's going to be, that's what the period we want it to be. So that's the time taken to complete 1 full cycle, and that's going to be equal to 1 on 40. And so if we rearrange that for n, we're going to end up with 40 times 2 pi equals to n, so that's going to be equal to 80 pi. That's our value for n. So n equals 80 pi. Now the other thing that we need in our x double dot equals to minus n squared x minus c equation is our c. C is the center of motion. So if we go back to the question, we see that we're going to have it says it's got a maximum height of 0.17 and a minimum height of 0.05. So because we've got a maximum height of that and a minimum height of that, the center is just going to be the average of the maximum and the minimum. 0.17, sorry, plus 0.05 divided by 2. Not bad. Divided by 2 gives us approximately 0.11. Not approximately, exactly 0.11. Yep. So then we've got all the ingredients for our x double dot equation. So x double dot equals to minus n squared, so 80 pi minus 80 pi squared, times x minus c, so minus 0.11. And it says for the maximum value of the force. So if we want the maximum value of the force, because the mass is constant, we want the maximum value of acceleration. And where does the maximum value of acceleration happen for simple harmonic motion? Well, that happens at the endpoints, right? At the center, it's got minimum value. At the endpoint, it's got the maximum. And we're going to consider the smaller endpoint because we're going to have a negative value multiplied by a negative value, which is going to give us a positive value. So that's going to give us the maximum. So we're going to get negative 80 pi squared. And one of the endpoints, the smaller endpoint, is 0.05. So 0.05 minus 0.11. And that's going to make approximately, if you plug in all your numbers, that's going to give you approximately negative 384 pi squared, not approximately, exactly, meters per second squared. And then because F equals ma, we can go ahead and substitute that in, or we can substitute that into the force equation. So mass of the object, they've said, was 0.8 kilograms. Yep, 0.8 kilograms. And then we sub in our acceleration, 384 pi squared. And that's going to give us approximately 3,032 units. And so we're done. Okay. Now, for the next question, okay, so the next set of questions involves discussing motion with and without resistance, and then projectile motion is pretty much just a combination of horizontal motion with resistance and vertical motion with resistance. So what I want to do is sort of discuss the different forms of acceleration. So we've got three main sort of forms of acceleration that's used to solve questions. So we've got d by dx of v squared on 2, v dv dx, and dv by dt. Make sure that you know these, because if it asks for a relationship between position and velocity, then you know that you're going to use one of these. If it asks for a relationship between velocity and time, then you know that it's going to use one of these. If it asks for position and time, then eventually you're gonna have to use this, and then v, since that's equal to dx dt, you're going to have to integrate again to get a position and time relationship. So make sure that you're able to look at what the question's asking for, and then appropriately choose which one of these acceleration expressions is best for them. Here's an example problem, but I think what we can do is do the next problem, because all it does is, this one's a bit more involved, so the other one's on the somewhat simpler scale of things. So this one involves using a different form of the acceleration. So here we've got an object of mass 1 kilogram and is projected vertically upwards with an initial velocity of u meters per second. It experiences air resistance in a magnitude of kv squared newtons, where v is the velocity of the object in meters per second, k is a positive constant, and k is a positive constant. The height of the object is above its starting point is x meters. The time since projection is t seconds, and its acceleration due to gravity is g meters per second squared. Find an expression for the maximum height reached by the object in terms of k, g, and u. Okay, first step for these sort of questions is to draw something called a free body diagram, where we're looking for all the forces on the object. So we've got the gravitational force acting downwards, right? Because it's launched vertically. So we've got mg acting downwards, and then since it's falling downwards, right? Since the object's falling downwards, since the object's moving vertically upwards, my mistake. Since the object's moving vertically upwards, the air resistance force is also pushing downwards on it, minus kv squared. So as the object moves upwards, because air resistance force acts to oppose the motion, the air resistance force acts downwards as well. So our net force equals to minus mg, so taking downwards as negative, minus mg minus kv squared, and that's equal to mass times acceleration. Now what's useful here is that the mass equals 1, so then it doesn't scale up any of these values, so all we're left with is minus g minus kv squared equals to the acceleration. Now, which expression should we use for the acceleration? Because it says find the maximum height reached, the special property of the maximum height is that the vertical velocity is 0. And so because we want height and velocity relationship, that means that we have to use acceleration as v dv dx. That's equal to minus g minus kv squared. That's the form of acceleration that we want to use. Then it's just a matter of trying to solve that differential equation. And these equations are actually separable, so they're not hard to solve. So we've got dividing through by v, we end up with dv by dx equals minus g minus kv squared over v, right? And then to solve that differential equation, let's flip both sides, sort of like fractions but not really. Dx on dv equals v over, and I'll pull out the negatives just because that's going to make things easier, g plus kv squared, and then putting all the x's together and all the v's together, we're going to end up with this dv. And then when we integrate that, that's going to leave us with x on this side. And to integrate this function here, I'm going to multiply through by, there's a negative here. I'm going to multiply through by minus 1 on 2k, positive 1 on 2k, and that's going to leave us with a 2kv up the top and g plus kv squared down the bottom. And the reason I do that is because now we've got the derivative of the bottom on the top, and that's going to leave us with minus 1 on 2k ln g plus kv squared. Okay, so plus c. Now to solve for what value of c that it is, to solve for what value of c is present, we're going to consider when x equals 0. So since it's launched from the ground, when x equals 0, the initial velocity they said was u. So that means that this value is 0, so c must be equal to 1 on 2k ln g plus ku squared. And so substituting that back into the x equation, that's going to make x equal to 1 on 2k ln gu plus ku squared minus 1 on 2k ln g minus kv squared. Sorry, g plus kv squared. Yep. And then combining the logarithms just to make things a bit cleaner, that's going to leave us with g plus ku squared over g plus kv squared. Now we could probably get rid of the absolute value signs because everything inside the brackets is going to be positive, but we'll do that in a second. So since it asks for the maximum height, we can say that the velocity equals 0 at that point. So at max height, v equals 0. So that's going to leave us with, I'm going to call the max height h, so 1 over 2k ln g plus ku squared stays the same because that's just all constants. And then since v equals 0, we're just left with a g down the bottom. And now that's definitely all positive, so h equals 1 on 2k ln g plus ku squared over g, and that's our expression for maximum height. Okay, so I hope that was all good. So yeah, that was it for mechanics. And like I said, with these sort of questions, it's just a matter of choosing which sort of expression for acceleration that you want to use or which one's most appropriate. For this question, where it's asking for a relationship between time and velocity, then you want to use dv by dt, and they've already hinted that in this question. So make sure that you have a look at this. This is from the 2020 paper, so have a look at that question, in particular drawing free body diagrams, but we're running out of time for today. But I will see if I can throw in the solution somewhere. Okay, so some exam advice. So make sure that as you're going through the course, I mean, we're towards the end of it now, but even during your revision, make sure to actually develop an understanding of the workings of each topic rather than just accepting or like blindly accepting or regurgitating common properties. So just like with the complex numbers, modulus, and argument stuff that we talked about at the beginning, instead of just blindly accepting that or blindly just regurgitating that, make sure that you understand why that's true. Either, like, I mean, what's best is a geometric approach, but algebraic approach, even if you're able to prove it algebraically, is still okay. But oftentimes, geometrically, you can simplify things. And usually with a visual or geometric approach, particularly with vectors, even 3D vectors, you can simplify things a lot instead of just having to go through the entire algebra. In addition to that, my main tip, it would be to say practice, practice, practice. Build up mathematical foresight, as my teacher used to call it. Just build it up so that you're able to see things happen before you actually do them. So be like, okay, I'm going to do this, and that's going to help me get closer towards the answer that I want, right? So if you're trying to prove something, have a look at what you want to prove, see which step or which approach is going to make it as close to possible as that, and then just go with that. And so be able to see what's going to happen mathematically before it's going to happen, right? But that just comes with a lot of practice. And if you're stuck with practice problems, rather than reading solutions straight away, so if you're doing past paper problems, rather than straight away reading the problems, particularly with extension 2 questions, just like see if you can find a hint on that problem, and then see if you can keep going accordingly. And then if you get stuck again, see if you can find another hint. But you will get stuck on exam questions, so make sure that instead of giving up and looking at the answer straight away, see if you can build up sort of an intuition as to go where to from the point that you're stuck. So yeah, definitely instead of looking at the answer straight away, see if you can find hints. In addition to just doing questions, I also recommend doing timed papers, particularly as you get closer and closer to the HSC, and so definitely start doing them now if you haven't done them yet. Do timed papers so that you can have so you can practice your exam time management strategies, see what strategy works best for you. Some people recommend, so there are different ways of going about these sort of things, but see what works best for you, and that just comes with doing the papers. Okay, so what about reading time? There's only 5 minutes of it, so it's not properly time to attempt every single question, but make sure you single out, or like you flag questions which you think is difficult-er, and which questions seem to be like just sort of easy marks-ish, or which seem to be sort of stock standard sort of questions. Make sure you're able to flag those, and make sure that you're able to note down, not physically write down, but make sure that you're able to see which ones are which, and then that will help you with developing your exam strategy. Start brainstorming ideas, not full solutions. So instead of maybe trying to do the actual question in your head, see if you can find ideas to solve that question. And that again comes with mathematical foresight. See if you can find ideas to solve that question, and instead of wasting too much time trying to solve a full question. Okay, and as I said, algebra, it is sometimes inevitable, and especially for proofs and mechanics, it can potentially occur through many of the topics. So sometimes you might have very long expansions, and especially with induction and things, sometimes you have a whole bunch of terms. So don't be scared to experiment. See if series seem to turn up. So sometimes geometric series might turn up, sometimes you might have a arithmetic series, and see if that simplifies things. But yeah, don't be afraid to experiment. Oftentimes a lot of things cancel. If you've got a messy expansion like that, oftentimes a lot of things will eventually cancel. So see where you can make cancellations. But yeah, be brave, experiment. But then again, keep your eye on the clock as to not waste too much time on the question. But most importantly, have fun. The content that you're covering in this course is extremely useful and extremely interesting. If you sit down and have a think about it, have a play with it, you'll see that these things are quite interesting, quite fun. But yeah, and even if you're planning to pursue a STEM degree further in the future, these things are very fundamental, extremely useful things that turn up a lot. So yeah, have fun. And any questions, feel free to put them in the chat, and I'll do my best to reply to them. And thank you. Thank you for attending my lecture.